though he denies it. He was a student here at UC Davis. He'll be around until Wednesday. He's a great expert in collider phenomenology, so make use of him while he's there. And he's going to tell us about simplified models for hidden sector dark matter.
Thank you very much. I'm very happy to be back in Davis. It's a wonderful place. I have lasers, yeah. So watch out. Yeah, it's great to be back here, and I'm going to talk about something that has nothing to do with collider phenomenology pretty much, but talk about hidden sector dark matter, and particularly hidden sector freezeout. So I'll set the stage for this, I hope, and I'll try to get everyone on the same page and discuss this in detail. This is based on work with Stefani Bori and Jesse Shelton that should be finishing soon. Hopefully by the end of this month, but we'll see how it goes. So, what do we really know about dark matter? If you're a cynic, the response is nothing. We don't really know anything about dark matter, and that's because of this guy here. Essentially what we have is some data that we push through our theory interpretation, and then out comes dark energy. So, dark energy is kind of a pretty galling thing to account for. So we have three possibilities. Either we explain this elephant, we find some flaw in our data, which honestly, given the precision of these experiments and how wonderful they are, I'm not too optimistic about this being any kind of solution. Or we fix the problem in our theory interpretation. So these are really the only three options we can have in moving forward to talk about dark matter. But I'm going to do the fourth option that everyone does and completely ignore the elephant for the rest of this talk and add to its inferiority complex. But if something is wrong in the data or there's something wrong with our theory interpretation, whatever we're saying about the properties of dark matter could change dramatically. So that's just something that's always bothering me, but I'm not going to really address the elephant in the room any longer.
But not on galactic scales, though, right?
What do you mean?
Well, on galactic scales, you don't expect dark energy to be important.
Right, you don't expect dark energy to be important, and I think rotation curves is actually one of the strongest, most compelling evidence for dark matter. But some assumptions we make about the local energy density are set by this, and that's reasonable. But if there were hypothetically some Mond-like solution that actually worked and accounted for dark energy, it might modify the properties of dark matter so that we have less or more than we think we do. So I do think that my own opinion is, even given dark matter exists. There's lots of evidence for it from many different sources. But I'm a little afraid that when we say that 27% of the universe is dark matter, we're making a bold assumption based on this other slice of the pie. But there is a lot of dark matter, we believe, and I think that's also probably true. There's a lot of evidence from CMB, supernova, and baryon acoustic oscillations that together give us a very fine measurement of this. Of course, back at the time of CMB, dark energy was basically irrelevant, and 63% of the universe then was dark matter, 12% atoms, and a lot of it in radiation. Dark matter is dark. That's another thing we know about it. If we place bounds on the mixing with a photon of how much the photon talks to dark matter, we know that has to be pretty small. So bounds range from 10 to the minus 6 to 10 to the minus 4 or so for this epsilon coupling connecting photons to dark matter. It isn't machos, so big clusters of baryons. We know that dark matter cannot entirely be machos. Some fraction of it could be, but that's pretty well established at this point.
How come that plot cuts off at 1?
Why does that plot cut off at 1? This particular plot from this paper cuts off at 1. There are other macho plots that show them showing constraints in other regions. I don't remember what they are. What's that?
Earth-bound black holes is still open according to some.
Primordial black holes are still open. Yeah, that's an option. But I thought those didn't fall under the category of machos, really.
From these observations, you wouldn't be able to tell the difference.
Okay. It's all right. The primordial black holes are usually around 10 to the 60 or so EV. I don't know what that is in solar
So
mass.
we haven't seen any, I don't know what it usually is.
Well, that's the models that are kind of predicting that are behind. Primordial black holes is a possibility, I know, but I don't know how that relates with the modular constraints. We know self-interactions are not huge with the dark matter. They can still be very large, but there is an upper bound on them, and one of the strongest constraints there comes from this nice bullet cluster, where in red you have the gas from the galaxies, and then here is the matter density from lensing, is in blue, and you can see that this one galaxy pushed through this cluster, and there's gas shown between them, but their dark matter just continues on and causes the lensing effects. We know it isn't too light. If we have bosons, we know it can't be lighter than about 10 to the minus 22 eV, which is a very, very tiny number, very tiny mass for dark matter. But that's essentially the point that the Broglie wavelength then is too large for it to really account for dwarf galaxies. Similarly, if it's a fermion, it can't be less than about 410 eV, because then you can't fit enough dark matter into dwarf galaxies just because of the Pauli exclusion principle. We also know that dark matter is not hot. If it had a thermal origin, it screws up structure formation and also screws up the Lyman alpha forest. And these constraints are pretty stringent, so around a few tens of keV is where the exemplar can say you can't have dark matter that's lighter than that if it was thermal in origin, so if it was at one point in equilibrium with the standard model, for instance. We also know it's quite elusive. Every shred of evidence we have for dark matter is gravitationally based. Looking in various methods, so production of colliders, we have standard model going to dark matter. Monojet searches have seen no appreciable excesses that indicate dark matter is there. In direct detection, we have a variety of experiments across a variety of mass ranges. So Lux is setting some of the strongest bounds now, and at lower masses, CMS light and Crest 2 are constraining dark matter, but we don't see it scattering off of anything, and we've got very strong bounds. Also, indirect detection, so dark matter annihilating in the either today or in the early universe, can cause imprints, and we do not see any evidence for those imprints either. So there's lots of ways we could look for dark matter, but everything's coming up null. Of course, there's a lot of options still, given that limited amount of information we really have on what dark matter could be. It could come from some higher theory, like supersymmetry, or extra-dimensional models, or Higgs, could be an axion, could be a sterile neutrino. There's a whole slew of possibilities, and this confusing map is definitely not exhaustive. All right, so today I'm going to first just review the idea of WIMP freezeout, so a weakly interacting massive particle freezing out. Then I'll discuss hidden sector freezeout, which will be the theme of the simplified models I'll present. I'll go into some detail about the Sommerfeld enhancement and what it really is and how it affects this story in particular. And I'll then discuss our two simplified models, a vector simplified model and a scalar simplified model, before moving to some future directions. And everything I'm going to discuss today is preliminary. We're still dotting our I's and crossing our T's, but we should be done pretty soon, so things might change a little bit. All right, so how do WIMPs freeze out? So the standard cosmological story in Excel is that after some period of inflation, there's a period of reheating, and then the universe gets to some high temperature and then cools adiabatically as the universe expands. And this expansion rate, Hubble, is proportional to the temperature squared over the Planck mass. So it cools very quickly. While this is happening, rapid collisions keep the standard model particles in equilibrium with one another. And because this is basically just a very hot plasma, thermodynamics entirely dictates the properties of the particles in that plasma. And a relativistic species has a number density that goes like temperature cubed, whereas a massive species has some number density that's proportional to this exponential. So as temperature gets low, this value gets very, very small because it drops below the mass, and then this number density depletes very quickly. So the idea of freezeout is any dark matter particle, really any state within a approximate Z2 symmetry, this falling number density causes the number changing interactions to eventually cease because the probability of finding another dark matter particle to interact with gets small because of this falling exponential. And eventually this falls below the expansion rate so that the sort of mean free path to find another dark matter particle drops to 0. And these number changing processes cease, and this departs chemical equilibrium and lingers around as a relic. So this is the story I just showed on the last slide, shown in the pictures. So this variable x, which is a time variable, going this way, goes to cooler temperatures, higher time. And this line here is the equilibrium density. So you follow this line until eventually you reach a point where your interaction rate is about right, and then you stop finding the dark matter again to interact with, and you just kind of flatline and head to an asymptotic value. And this value happens to be around the picobar times c. And if you have a smaller coupling, this freeze out happens earlier, and if you have a larger coupling, it freezes out later, and you get not enough dark matter. But the WIMP miracle then is this observation that if you have a weak scale coupling strength over the TeV scale roughly, you're going to have a cross-section that's around this value. So this seems to make a really nice story for the origin of our dark matter. We have a TeV scale mass, this interaction, and we can get dark matter from that. And moreover, lots of natural motivated models like supersymmetry have a perfect candidate here in the neutralino. So this is a very nice story. Unfortunately, there's no evidence of supersymmetry with top partners or anything else from a slew of LHC measurements that have found nothing beyond the standard model so far. Supersymmetry WIMP parameter space is still a little remaining, but the outlook's not too great. You're living in corners now. And of course, we could find a WIMP there tomorrow, but it's looking a little grim. So instead of requiring some high structure, you could imagine just taking some renormalizable minimal model, where you basically just take the standard model and glue on some dark matter particle that talks to the Z or the Higgs. And these models are getting heavily constrained. There's some territory that remains, but not much for too long. It's really a closing parameter space for dark matter of these minimal varieties. So perhaps the WIMP miracle is a red herring, and this nice coincidence of scales and coupling strength is really just a ruse. So as a minimal idea, you can imagine keeping the thermal freeze-out story, this nice history of the universe that gives a nice origin to the dark matter, but we just ditch the weak scale. So you could imagine, for instance, having some new electrically neutral dark particle, a scalar, a fermion, or a vector. Then if you write down all the couplings of this to the standard model that are dimension less than 4, you get these 4 possibilities. If these froze out and have the coupling strength to cause them to freeze out, then there's no Z2 protecting this state, and it will just decay. So these are not valid dark matter scenarios here. This one's in principle a viable model, but it's pretty well constrained. This was what I showed on the last slide, this is one of the possibilities. And there's not too much hope for this to last beyond xenon 1 time. All right, so one step more complicated than this standard WIMP story is hidden sector freeze-out. So we take one of these couplings here, and we have the dark matter in its own sector, and it freezes out into some hidden sector particle, either a vector here or a scalar phi.
So can you just go back to that? I just went by really fast. So you're just analyzing some low dimension operators to
in this
have
paper.
some higher, have some higher dimension, just some freeze out the standard model.
Yeah, they had basically they introduced couplings. I just selected the ones that some of these are actually not.
So that was just the same thing. Okay.
Yeah.
Okay. I thought you were. Okay.
Yeah. There's nothing new added here. It's still the same thing.
Still
on
the
the
same
previous slide.
Mm-hmm.
It's a nice paper, but thank you for the properties.
Mm-hmm.
Yeah. So the hidden sector freeze out is kind of the next step. If the leading order WIMP is the story I've been telling so far, this is kind of the next to leading order WIMP. So essentially in these models, what you do is you introduce some dark matter particle, So here we have a direct fermion. We have a vector mediator that talks to the dark matter directly through this coupling G-dark. And then there's the portal coupling we introduced to connect the two sectors, the hidden sectors, to the standard model. Similarly, in the scalar model, we'll have a Majorana dark matter particle talking to a scalar with a Yukawa interaction and this portal coupling connecting the two sectors. So now this interaction strength, G-dark or Y-dark, is what's setting your relative abundance. This freezeout, this sort of left half of this diagram, that just happens for free. And this process is valid as long as the dark matter is greater in mass than the two vectors. In principle, you can actually have the dark matter mass be slightly less and live off the thermal tail, but everything I'm going to talk about is assuming that the dark matter is heavier than these states. This epsilon portal coupling then thermalizes you with the standard model and allows the state to decay and dump its entropy back into the standard model so that you don't have any hot relics.
It's not just that it thermalizes, you actually assume it decays.
Yes, it does. I mean, you get both of those with the standard.
Assuming V or phi decays, but not necessarily chi.
Chi does not decay, yes.
Yeah.
Chi definitely does not decay. Chi has an exact C2, but the portal coupling allows for the other states to decay. If, in the case of phi, it needs to go there, which it does. All right, so our two models are this vector model, where we have some free parameters that boil down at the end of the day, including the portal coupling, to the mass of the dark matter, the mass of our mediator, mz dark, or alternatively this mass ratio between these two, and this portal coupling. This value of G dark is just fixed by relative abundance. It's some value like 0.1 or so that depends on what the particular parameters are here, but that's completely fixed by getting the correct relative abundance. Similarly, in our scalar model, we have three free parameters again: the dark matter mass, the mediator mass, and this mixing angle sine theta, which is proportional to the portal coupling. And again, this coupling is just fixed by the relative abundance. So there are various ways that we can, in principle, probe these models. So first, the relative abundance fixing this coupling is set by the combination of Planck, supernova, and baryon acoustic oscillations. And there's no sensitivity at all to epsilon in this process. Epsilon is completely removed from the story as long as you are thermalizing. Indirect detection proceeds through the exact same diagram, essentially, and you can see indirect signals of Fermi, AMS, Planck, Sommerfeld telescope, and others. And there's no suppression on these. They are independent of that. Direct detection, on the other hand, you get from Lux, CDMS Light, Press 2 currently. There's a lot of future experiments proposed here, and that's proportional to epsilon squared. So as portal coupling gets small, these signals deplete. Colliders, in principle, you could produce this at Atlas and CMS, and this would be suppressed by epsilon squared, producing the dark matter. Also, you can produce the mediator directly and not produce the dark matter, and that can place constraints from precision experiments, including LHCb, Bell, CHARM, E949, various experiments. These are proportional to epsilon as well, but they're targeting the mediator, so that there's a different handle that you can access. Okay, so
The indirect detection is independent of epsilon because
yes.
the decay has to be rapid enough for cosmology that it's essentially prompt on
Right.
galactic or something scales.
Yes.
Yeah.
So
Right.
that's
it
true.
decays before it escapes the galaxy or something.
Right, and that we kind of get for free because of the fact that our parameter space is bounded.
Yeah.
So here's the vector model. I'll discuss these plots in a bit more detail. And here's the scalar model. So in the vector model, this is T freezeout versus the portal coupling. And for a large enough for a small enough portal coupling, it's kind of hard to read on this projector, but this is never in thermal equilibrium. So if the portal coupling is too small, the standard model and the sector are never in thermal equilibrium with one another. And while in principle there are valid models that live below this line, it's no longer the simple thermal freeze-out story where the temperature of the two sectors are equilibrated. At higher portal couplings, you are in thermal equilibrium during freeze-out, and the story is completely predictive using standard machinery. Similarly, in the scalar model, we have regions that look somewhat similar, except you now have this green region where the sectors thermally decouple. And what happens here is the temperatures of the two sectors were at one point in equilibrium, and then as you cross these mass thresholds, the bottom quark, for instance, falls out of the plasma, the dark mediator loses its contact with the standard metal. So its temperature was set at one point, but then these two sectors drift apart. And they can assume slightly different temperatures from one another because of that.
Are there really models where epsilon is below, viable models where epsilon is in that blue region
So
with no other new physics?
no other new physics.
So just in this model, are there regions, you're saying there are regions of parameter space?
So we have not
Smaller
explored this region here, but in principle, freeze-in dark matter is something that lives in this region. If there's strong interactions, or strong enough interactions between its own sector, you can thermalize that sector independently of the standard model and freeze in through the standard sort of process to do so. And then you can live in a territory that you're going to require a larger dark matter mass typically in order to freeze in and have a satisfactory story. Alternatively, you could separately populate this by having an inflaton reheat the two sectors in different ways. That's a more complicated story.
And so what's the dark matter mass in these plots?
So the dark matter mass, T freezeout is typically dark matter
T-freezeout is
over
typically-
about 20. It varies a bit, but that's...
Right, okay. Right.
So there are three free parameters, this dark matter mass, the mediator mass, and epsilon. Epsilon is bounded and has to be greater than these values in order for our story to be satisfactory. Again, you can construct a model that lives below here, but it's tricky and requires additional machining. So this bound is just requiring that the two sectors thermalize. There's a couple other bounds we get on this parameter space. So first, we're requiring that our dark matter is greater than our mediator mass, so we have the nice hidden sector freezeout story. So this ratio of masses is not greater than 1 here. There's some constraints on unitarity. If the dark matter is too heavy, then the couplings you need in order to get this to freeze out appropriately have too high of a value so that you're no longer prohibitive. So this is around 50 TeV, maybe a little higher, maybe a little lower, but roughly that's putting an upper bound on our parameter space. Additionally, the mediator has to be greater than twice the electron mass. And this is for several reasons, but mainly that it doesn't disrupt BBM. In both the vector model and the scalar model, if the mediator is lighter than the WIMPless mass, the decay length is long enough that either BBN is disrupted or some other constraint enters that completely fills the scenario. So that creates this sort of diagonal line here. The fact that direct detection bounds exist, combined with this bound on epsilon, actually puts a lower bound on our parameter space, kind of in excess of the union of these two. Additionally, there's sort of two other constraints that enter.
So what's the detection mode there? Sorry, just
Direct detection.
yeah, what?
So this is spin independent direct detection.
Just
and
from
the scalar
just
and
by mediated by the dark Z?
Yeah.
Okay.
So either the dark Z or the dark Higgs. Yeah. So I'll discuss those in a bit more detail later on, just setting up the parameters.
And so the mediator bigger than 2e, that's just requiring that the lifetime of the Z dark be sufficiently short. Is that right?
Basically, yeah.
Okay.
There are some, in the scalar model, there are actually a bit of constraints beyond this on the mediator that I'll show in the plot later. But yeah, essentially that it's short enough that it doesn't disrupt BBM. Additionally, there's the current generation of experiments have the dark matter mass greater than 500 MeV for them to have sensitivity typically. That's not always true, but in direct detection, Fermi and AMS is actually even above this. But the current generation of experiments don't go below this sensitivity. So although this parameter space in this way is completely an okay place to live in principle, our experiments aren't accessing it now, so I'm not going to talk about it further in this talk. But this is certainly an interesting wedge here in this triangle. Lastly, there's, in addition to our unitarity constraints, there's constraints on our, not really constraints on our dark matter, but our modeling of the region at high masses starts to break down because of the Sommerfeld enhancement. And Sommerfeld enhancement affects freezout, and in this region, freezout is affected too much, and I'll discuss the Sommerfeld enhancement now in a bit more detail. So, for those of you who have never heard of the Sommerfeld enhancement, it's essentially anytime you have light mediators and low velocities, then your cross-section gets this effect where you have sort of ladder diagrams that are summed in order to contribute to the annihilation. And this is somewhat a kludge for the fact that these are kind of roughly getting closer to forming a bound state, but it's basically a non-relativistic quantum mechanical effect from the two particles feeling one another's potential, and since they're non-relativistic, this matters a lot. It's largest at small velocity v, small mass ratio or large mass hierarchy, so the mediator is much larger than the dark matter, and also for large coupling strength alpha. And this contributes both to S-wave annihilation, proportional to velocity to the 0th power, and P-wave annihilation, proportional to the velocity squared. So both of these get a Sommerfeld correction. So what do these actually look like, the Sommerfeld enhancement? So here I'm just showing the S0 on both sides for a given choice of parameters. So there's 3 parameters and that S depends on: alpha, the ratio, and V. So the mass ratio here is what's shown on the x-axis. The y-axis is the value of the Sommerfeld enhancement for velocity fixed to 10 to the minus 3 and varying the value of the alpha. So you see for large alpha, you get these very sharp resonances in the Sommerfeld enhancements. This is several 5 orders of magnitude enhanced in some places. There's kind of an umbrella covering this. And right around the time you get to the value here of the mass ratio equal to the value of the velocity, this flatlines and becomes just the massless Sommerfeld enhancement case. For lower couplings, you get the same sort of resonances that are a bit more spread out and don't peak quite as sharply, but you still have the same sort of umbrella covering it. And as you go to lower and lower cross sections, or lower and lower couplings, this becomes less and less important of an effect.
So how I see. So I can somehow think of those peaks. The reason those positions of those peaks depend on alpha is that somehow there are would-be resonances whose energies are controlled or affected by the coupling.
Yeah, sort of. Yeah, it's
something like that.
It's a little gummy in the interpretation. Yeah. So similarly here, now just shown in different axes, where you have the coupling strength here, which is roughly fixed. This value alpha is roughly m pi, really over about 40 TeV. But that's just sort of parametrically wherever it corresponds to in the particular story. And you can see that for decreasing mass ratio, so initially you start here, and this one, the resonance structures would kind of be appearing beyond here. They'd be even larger, but you don't see them. Then when you get to the -1, you see very sharp resonances. When you get to -2, you see more subdued but more frequent resonances. And for -3, you can barely see any resonance structure at all. It's a little wiggly, and that's because this mass ratio has dropped to the point where it's about the velocity. And for 10 to the -4, it's completely flat. Or not flat, but straight line, no resonances.
Is the left plot for vector and the right plot?
In both of these are actually for the S0 plots. The S1 is proportional to the S0, and some additional contribution is just slightly larger than the S0, but it's also velocity suppressed, so there's a trade-off. But it's larger by 10%, not by orders of magnitude. Of course, the variation in alpha and m is very important, but the velocity, as for any model, as you go to lower values, the velocity just increases, or the Sommerfeld enhancement increases monotonically with decreasing velocity. So that you can see here for different values, for a single value of alpha and different mass choices, no enhancement. You get an enhancement up until about the mass ratio. Similarly here, about the mass ratio, about the mass ratio, about the mass ratio, and you get a faster. But it increases monotonically with velocity. In other words, the fact that you're living on a resonance is a property of these two parameters, is not a property of velocity. showing just for a different value of alpha, you can see places where you're probing resonance directly here. So this -1 is on a resonance, and as is the -2, and these spike significantly relative to this case here, where you wouldn't expect too much change. But the Sommerfeld enhancement affects several things. So first, it affects the annihilation at CMD. And in this case, the sort of critical velocity that enters in these expressions is something like 10 to the -7. And because of this fact that things flatline once you get to mass ratio, basically the mass ratio, velocity is that low. And we're not ever looking at mass ratios down to 10 to the -7. It doesn't really matter what parameter you put in here. If it was 10 to the -8 or 10 to the -10, it wouldn't change anything.
Why is the velocity so small then?
At recombination. So no structure has formed. So today dark matter is virialized, which is what gives it its velocity. But here it's just redshifted from a very high temperature. So it has pretty much no velocity anymore. Everything's stationary, essentially. There's some overdense regions and so forth.
But where does 10 to the -7 come from? What is...
10 to the -7 is an upper bound from requiring that. So it could be much less than 10 to the -7. But this is from a sensible story for the kinetic decoupling of the dark matter from the. So in addition to the chemical equilibrium and the number changing process, you can also continue to thermalize the dark matter in principle if it has some non-number changing process that's large. But that itself has to be coupled based on the constraints from the CMB. So you can use those to put this up or down. There's a paper by Torsten Bergman and company that where we got this value as an up or down. I forget exactly what the parameter is that enters that causes that, but it's typically much lower than this. In the Milky Way today, because of the virialization of the dark matter, the bound is roughly something less than this value, and we're taking sort of the upper end to be conservative, but 1.7 times 10 to the -3. This corresponds to 500 kilometers per second. In dwarfs, 10 to the -4 is sort of the upper bound typically. Some dwarfs have a lower value, 10 to the -5, but we use 10 to the -4. And lastly, freezeout can also be affected by having this velocity is roughly square root of 6t over m cap. And that can be appreciable. So here on the right, I have a plot of different mass ratios and velocity now of 0.8. So this is the relative velocity, so it's really v1 minus v2 absolute value. So it ranges from 0 to 2. But for 0.8, you can see there's still an appreciable effect. And you can, for large couplings, get a Sommerfeld enhancement of about 4, which can significantly change your freeze-out story. And because it's greatly perturbed, and moreover, instead of using a fixed velocity here, you should really be sampling over different velocities. And what we found is that using a fixed value instead of sampling over a distribution is valid as long as this condition is satisfied. This is empirically determined, but if the value you get from doing the freeze-out calculation with alpha, or without alpha, and with alpha differs by more than 2, or sorry, with the Sommerfeld, without the Sommerfeld, if that value of alpha differs by more than 2, then this approximation holds. If you go deeper into that territory, where this is much greater than 2, this approximation does not hold very well, but there's not much dynamically interesting in this range, so we're not too worried about our inaccuracy in modeling there. But we'll denote that in the plots that we don't trust this for. Before I move on to the vector model, are there any questions about Sommerfeld? Okay, great. So our vector model, again, comes from this Lagrangian and has 3 free parameters, basically: the dark matter mass, the mass ratio of these two, and this value epsilon. So one of the first ways to detect this I'll talk about is indirect detection, which has taught us a ton about pulsars. And there are several different sources that you can, in principle, indirectly detect the annihilation of dark matter in the universe. So Fermi looks for photons, and They have a nice study where they look at 41 different dwarfs across a bunch of energy bins, and they make measurements and place constraints on some models. So we extend their argument and use the 41 dwarfs and combine them in a statistically sensible way with the energy bins to place a constraint. And it's a little hard to see in this projector, but this 1 picobarn C value is shown here. So this is the maximum allowed value given given our model. This is the maximum allowed value on the annihilation rate. So the red region here and here, this is probing into the Sommerfeld Enhanced region, is illustrating where the current maximum allowed value is exceeded by the Sommerfeld Enhanced annihilation cross-section. So in other words, everything in the red here and here is excluded. The green is when the mediator is greater than twice the electron mass, and this brown here, which is also a little hard to see on this projector, is the Sommerfeld condition, where this value disagrees by a factor of 2. So going further into this region is less reliable, but doesn't affect control. In addition to Fermi detecting photons at dwarfs, you can have positrons from AMS. So AMS is the alpha magnetic spectrometer orbiting the Earth and detecting all kinds of things, including positrons. So if dark matter annihilates in our local area and comes to us, case to, we have this dark vector decaying to 2 electrons, we can pick up the positron from that signature, and that is shown here in this orange band here. So this orange band constrains the dark matter annihilating.
Sorry, I just lost track. In your plot,
Yes.
You're not showing this as a function of epsilon, so epsilon is fixed.
So because indirect detection is completely independent of epsilon.
Oh, I'm sorry, that's right, that's
Yeah.
the point. That was the point. Yeah.
So these bounds are robust and apply to our model down to the floor.
Okay.
So additionally to Fermi and AMS, the injection of any kind of energy pretty much during the time of recombination, when dark matter is moving very slowly and annihilating very freely, can create spectral distortions in the CMB power spectrum. This can be seen in SBT, ACP, other experiments. But almost no matter how it decays, it's going to inject some energy into the CMB that screws this up. So we combine all possible decay paths through the description of Tracy, who I have learned that Tracy is law when it comes to indirect detection. But the Planck bounds, again, a little hard to see on this projector, are shown in the Sommerfeld resonances, and also go down here to roughly 10 GeV at low masses, and then a little near the threshold it gets a little worse, so down to 4. So essentially everything here in our model is constrained, or excluded. So you still have allowed territory up in here, and in these little gaps between the resonances. And that is what is currently allowed and currently excluded by indirect detection. So in addition to indirect detection, there's direct detection. So this is looking for the dark matter in big vats of xenon, for instance, here on Earth. So the dark matter nucleon cross-section can be written in this way for our model here. So this value, G dark, is set by the relic abundance. Those are our portal coupling epsilon. This is the reduced dark matter nucleon mass. And these are the effective Z dark nucleon couplings. And it turns out that when you combine these, the dark vector only really couples to charge of the nucleus. So it's independent of A, and only depends on Z. And this is inversely proportional to the mediator to the 4th power. So as you go to lighter and lighter mediators, you get more and more sensitive in these experiments.
That's a result of the fact that you're coupling through the Z, the fact that you're proportional to the charge.
It's actually not the Z. So there's a paper very recently by Felix Yu and some other people that found this. We found it shortly after, I guess they did. But we were kind of stumped by this for a while. But it's, I guess, if you have two massive mediators, the way your mixing matrix works out, you kind of cancel off everything that the lightest, the massless guy does not couple to. It's
massless guy, meaning
the photon. So when you combine this three-dimensional mass matrix,
but the reason it's determined by the charge is the fact that it's a ZZ dark mixing, right? So you're saying that
Easy there.
yeah, essentially this guy here,
it's just not obvious to me. That's why I'm asking.
it is not super obvious.
Yeah.
We were stumped on this for a very long time. But essentially what happens is this guy destructively interferes with this guy so that it exactly makes a piece that does not couple the charge. I can show you their cute little...
I believe you. I just
Yeah.
want to understand why that would be true.
The quiz helps with that type of thing. I'm not going to be able to quote it a way to explain it out here.
Okay.
So we can reorder this and treat this as a bound on epsilon. So epsilon has to be less than the value we determine from experiment for the particular dark matter mass times these expressions, which again, epsilon is going to be proportional to mc dark squared. So current constraints can then be translated into our plane here. So mz dark over m chi versus m chi. Here's this Sommerfeld region where we don't trust our modeling. And this is the bound then on the upper bound on the allowed value of epsilon from direct detection. So we have 10, 1, 0.1, and so forth, decreasing. And this is the region that's most sensitive here, is right around 10 G, close to where this bottoms out. So this information then can be combined with our bound from the thermalization condition. So that essentially to generate this plot, what we've done is calculate the collision term for sort of the one-sided collision term where we have a z dark coming and hitting anything in the standard model and interacting with it. So you have z dark something going to 2 of anything else. And that will indicate when the two sectors are in thermal equilibrium if this value is equal to Hubble, or if this value is greater than Hubble. So we do this for several of the most important processes, ignoring things that happen above the electroweak phase transition, because that's a lot more complicated. But what we find is this nice decreasing curve. And this then, given our value of T freezeout, which is roughly m pi over 20, can be translated to show where this model is no longer valid based on direct detection placing constraints. So everything in this blue region is essentially excluded in our model by direct detection. So combining this with the indirect detection contours, you can see what the remaining parameter space looks like. This clips a little bit off here, but as direct detection gets better, this blue curve would move up into this parameter space and cut out more regions. Basically, all of these curves would shift upward and outward.
Sorry, why?
Yeah.
So sorry, I guess I haven't understood why the blue. I haven't understood the blue region. I guess.
The blue region?
Yeah, because somehow it is. It's excluding small epsilon.
Yes.
So what's going wrong there?
So what's going wrong there is we were never in thermal equilibrium.
Oh, it's just a freeze-out story.
Yeah.
But then why did you say that direct detection is going to increase the size of the blue region?
So so what actually happens is as direct detection gets stronger, all of these contours would shift up. Now this picture here that's sort of straddling -8 across this region is going to stay in the same place. It's just all of the curves are going to move upward as direct detection gets more sensitive. So as you know, you go to your Darwin, for instance, you're going to drop the sensitivity by 2 orders of magnitude, and 4 orders of magnitude, and this bound will then go down by orders of magnitude. So the allowed value of epsilon.
So you're pushing down. You're ruling out those large epsilons in that platform,
No, you're ruling out the small epsilons. So everything below 10 to the -10 here is excluded by direct detection. In other words, your direct detection experiments are sensitive to this model, this parameter space here. They're living at 20 GeV and roughly 4 MeV mediator, or 40 MeV mediator. You'd be living here, and then you can't have an epsilon value above 10 to the minus 10, or direct detect. You would have seen it in direct detection. Make sense?
Right.
So then, using that information, we can combine that here to say, well, if we have to live below this value, then this parameter space point is not consistent with the story that we froze out while thermal equilibrium with the standard model.
Why don't you have contours from direct detection currently on that plot? Are they just off the plot?
These are contours from direct detection.
Where are the current bounds?
Define current bounds.
From lux.
So lux, so you can actually kind of see the shape of lux here, and then lux goes to CVMS light, goes to crest, and that's just what's shown here. Okay. So essentially, from this bound, we can translate this bound into a bound on
Right.
epsilon, right?
Yeah,
So what's being shown here is just a bound on epsilon. Because for a larger epsilon value, you'd be more excluded. For a smaller epsilon value, you'd be more.
Okay.
And then that can then be combined with this constraint to say that everything in this region is just not valid in our model.
Okay, I've got it.
Interestingly, in these models, as you look to the future, so Darwin, the super, I guess, extra next generation LUX type experiment would be probing close to this xenon neutrino floor. Whereas, in principle, our model has lots of valid territory well below the neutrino floor. And that's one of a lot of the more standard WIMP scenarios don't really have much ability to access any territory down here. Whereas in this case, there's wide open territory, and that kind of motivates new technology that can, in principle, extend beyond the neutrino floor.
Not even just pure Beano can go down there with no problem.
Hmm?
I thought just pure Beano dark matter can go down there with no problem.
The pure Beano, there's spin-dependent interactions with pure Beano, but it's sort of on a different plane. But that's maybe that can't access the neutrino floor.
I thought
Or against it.
yeah,
I know in pure Higgsino, or close to pure Higgsino, there's a region near M Higgsino of M Higgs, right in that territory, where there's a gap and that can imprint. There's only an upper bound on what the cross section is. They don't know what it actually would be. This is from the steady calculations of Richard Code. Okay, so in addition to direct detection and indirect detection, you can imagine looking at colliders or in precision experiments for these models. So looking in like monojet signatures for direct production of dark matter is heavily suppressed because not only do you have this epsilon squared value, but you have to produce this through an off-shell mediator in order to access it. So that's really a very poor way to get at these models. But there are many existing constraints on the mediators. So a kinetically mixed dark photon. Let me just show you what's going on in this plot. So up here is LHC constraints on the mediator from drone GaN production and extra weak precision. Once you get below the upsilon threshold, you have constraints from Babar and Chloe and NA48 and some other little experiments. This here is beam dumps, a series of beam dumps throughout the years. E137 and so forth. All of them have silly acronyms like that. And here's the most recent constraints from Supernova 1987A by Ruben Essig and Sam McDermott and company. And then there's these little blobs down here for BBM constraints that just kind of float around for some reason. So how our parameter space kind of maps onto this, it turns out anything below 400 MeV in dark photon is excluded by indirect detection. The combination of AMS2 and Planck, there's no viable parameter space where you have a dark mediator lighter than this. direct detection up until the Sommerfeld restricted line excludes this territory completely. And this sort of Indiana-shaped region is a combination of the two, is able to constrain, cut that out. So you're left with this golden territory in our model. And this little green line is the future direct detection sensitivity, including it's Darwin and Crest 3 phase 2 that's able to cut into this territory as well.
What does it mean that the combination excludes them when each one individually doesn't exclude them? What's going on there?
So what's going on there is, back to this spot. So essentially the point where you can get down to 400 MeV in indirect detection is right here. There's nowhere else on this plot you can do that. But basically what the combination does is it forces you, if you're trying to live here, then that tells you what the upper value on epsilon is. So this, the direct detection, indirect detection tells you where you might potentially be living. But as you go to as you try to live in a higher value of epsilon, it's constrained then, and that's what carves out this region. Okay. So if the bounds from Fermi are improved, or Planck are improved, it'll push this way on this plane.
Okay. So does that red region continue down at
It's tricky to say because we don't have the story for what really happens there. If you live down here, you're never in thermal equilibrium, and you must be populated through some freezing mechanism.
Oh,
so in principle,
the white region is decoupled. Sorry.
Yes, everything below this is decoupled. Yeah.
Good.
Yes. Yes. So this is the sort of territory that, in principle, will be could be accessed in this model, but direct detection is clearly one of the best avenues to pursue this, because trying to find 10 to the minus 4 mixed dark photon at LHC is going to be very challenging. So if you were to, for instance, be living in this point in parameter space, and direct detection tells you this is where you are constrained to be, you can't be above that, then really you're constrained to be down here. So I'll just illustrate on the next sort of our master summary plot what's going on. So in green, so up here, here, and here, what's going on is the constraint on the mediator is more stringent than the constraint on direct detection. Again, everything from Fermi, AMS, and Planck are completely excluded in this model. Then we have the thermal decoupling story, which is sort of a breakdown of the treatment of our model. The thermal freezeout in the hidden sector does not work anymore, and Sommerfeld condition is here. So this leaves a lot of wide open territory that can be accessed in future experiments. So that is the vector model. And one question immediately is, if this is really a simplified model, how generic are the features of the model? So you can imagine different sort of deformations you could add to your simplified model and see how the story gets affected. So if we were to add additional heavy states, this would have no effect typically. In principle, it would thermalize you earlier on, but if the portal coupling is where it is, then it's really going to do nothing. So additional heavy states is the most innocuous addition we can add. If we were to add additional dark matter for some global symmetry, could increase the coupling we calculate a freeze out and get slightly stronger direct detection limits, but it's not actually going to change much qualitatively. Similarly, promoting a vector to a V-A coupling doesn't really change anything qualitatively. If we add a dark Higgs, so here we've used a Stuckelberg mechanism to give our photon mass, but if we were to add a dark Higgs, it would be irrelevant if it was an additional heavy state, but if it's lighter than the dark matter, freeze out, that can affect the story. So in all of these scenarios, very little is really changing though, as long as the dark Higgs is not dominating the story. So that's a good thing. These are very sensible deformations we can make in the model that don't change things. If we were to make the dark matter a Majorana particle, or a pseudo-Dirac state, so that there's very small splitting between two Majorana states, this is going to reduce our direct detection efficiency because spin independent is turned off, and spin dependent or inelastic scattering. Now, where things get really bad is if we add new light states. So if we add a new Z2 charged light states, so some new dark radiation or something, that can change our dark matter story a lot and add constraints or be constrained by other things. Similarly, adding a state that's not charged under a Z2, but something you dump energy into or entropy into in the real universe, that can change the story qualitatively. And of course, Z dark to invisible decays will weaken our indirect detection bounds, but in order to do that, we really need additional light states. So that's modifying things in the same way as here. But the sort of observation from this is that the simplified model story that we're selling here is really for the freeze-out story. And if we introduce some physics that's changing our freeze-out story, that's going to have a very large impact. But if we do this minimally, it's going to have minimal impact. So essentially, our simplified model is fairly robust up to this Majorana and pseudo-Dirac scenario, as long as our dark vector and dark matter are the two lightest states of our heat sector. So in that sense, this really is a simplified model that's accessing, that's covering more territory than just the model alone. All right, so I'm going to quickly go through the scalar model, which parts of it are a bit simpler, and parts of it are a bit more complicated. You've seen a lot of the details so far, so it'll be easier to go through. So again, three free parameters, and chi, the mediator mass, and this mixing parameter that is measuring basically how tightly connected these two sectors are. So fermionic dark matter annihilating into scalars is a p-wave process, meaning it's proportional to the velocity squared. So naively, you might expect that this has no constraints because the velocities are very slow today, slower than CMB. But there's a nice paper by Haipeng An, Mark Wise, and Yue Zhang that was pointing out that you can actually form bound states of dark matter particles. So dark matter comes in, finds another dark matter particle, and as long as the binding energy of this is less than the mass, or sorry, the binding energy is greater than the mass of the mediator, you can, even at very low velocities, emit a mediator and form a bound state. So this only happens at high couplings and large splittings, but it's a viable scenario. And these bound states can happen at the time of recombination for CMB, and then these bound states can decay. And that results in these rapidly oscillating sensitivities, depending on where, when these bound states are being formed reliably in the model or not. But you get constraints here, and then in the moment, a small deviation to a lighter mediator, and we have no constraints. You have constraints again, we have no constraints. So this structure results in these sharply oscillating lines here of constraints for formation of different bound states.
So why wouldn't this happen in the vector model?
It would happen in the vector models, just the vector models. These are essentially the positions of the Sommerfeld resonances, and it's very narrow. So in the vector model, you also have this, but Planck's already excluded it because this process is subdominant to the other annihilation process. So there's the Sommerfeld condition from the p-wave freeze-out. So this is actually a bit larger and more important than the S-wave process here, whereas everywhere else Sommerfeld is less important for the p-wave process. And here we have the mediator being greater than twice, or being less than twice the electron mass, so that's excluded. And, or not all have that again. And here we have the perturbative decoupling going on perturbative. So this is sort of the only effective indirect detection, but it's an important one. And basically, a little below this plot is where these lines become perfectly dense and we kind of extend into this region here, and everything's excluded. So again, we have an expression for direct detection, and we can use this to place a bound on sine theta. In this particular model, there's, if the scalar, the mediator, and the standard model Higgs become close to degenerate, you have a completely destructive interference. And this is essentially because you can have a very large sine theta, even for a very tiny epsilon, when these get close to one another, because the sort of degeneracy pressure pushes them apart. And you get total destructive interference. So this is again proportional to 1 over the mass cubed, or to the fourth side. So, writing this in terms of a bound on sine theta, and using the direct detection constraints, again, we find a very similar behavior. Here, things cap out because of the structure of the coupling. And here's where you're very close to the Higgs in mass, and the direct detection becomes completely insensitive. But the bounds are, again, most sensitive in this region that we're about to find. So we can, again, compute the collision cross-section, or collision rates, and for various processes, including this SS going through an on-shell Higgs into two bottoms, usually. And that affects things substantially at low freeze-out temperature, because it's kind of what's driving this curve here, but otherwise has a very small effect. So essentially what we have then is this region where you're in thermal equilibrium during freeze-out. You're never in thermal equilibrium here, and here the two sectors are allowed to decouple. And if they decouple, their temperatures drift in a controlled fashion, despite the evolution of the G star. And shown here in blue is this never in thermal equilibrium region, and here in the sort of darker blue dash is where the sectors decouple. And in this region, you shouldn't really trust our freeze-out calculation fully, because we do not properly account for this. So here there's a lot more territory allowed. In particular, there's no longer robust Planck constraint. You can go to much lighter masses. And here we're requiring that the two things are not too close in mass, so that we're cutting out this region. But this is what's allowed, except for these very sharp regions where you're right on resonance with Higgs. And there's a lot of territory, again, below the neutrino flow that in principle could be accessed in some next generations. Right? Now again, production of monojets and so forth is suppressed at colliders. But there are many constraints on the mediators still. So one opportunity to access this is from exotic Higgs decays. So the branching ratio of Higgs decaying to anything exotic is, well, it's constrained to be less than basically a third, and that's what's shown in the gray line here. Higgs to two scalars going to 2mu, 2b. There's everything in this green here, and tau is there, and here's 4mu, which is actually a very tight constraint when you're below the threshold value. And there's also then direct searches for the mediators. So you can look for light scalars in a variety of experiments. So here's Higgs searches at LHC, LEP constraints on this in the mediator in association with the Z. You get constraints from LHCb and two different searches of theirs where they look for B to K mu and B to K star and a scalar which can then be long-lived, and they get very tight constraints on the gravity space. K to pi nu constrains things at low mass here, and the CHARM beam dump experiment accesses here. SHIP is a future beam dump proposal that will cut out a lot of this territory. In addition to looking at this at various precision experiments, there's also cosmological constraints on this from DBM. Having a light scalar couples to the electron below the twice the muon threshold. It has a very long lifetime typically, and its entropy injection at late times can dilute the N effective value, or A to B, and gum up BBM, or the observed value of N effective. So this territory is all kind of cut out. There's, in principle, some constraint from supernova 1987A, but this is not well known what this actually is. And the existing studies that have looked at this have not done it correctly, so it's unclear where this constraint would actually be. All right, so now combining these constraints on the mediator with our constraints from direct detection, you can see a large bit of territory is now more constrained by the direct searches for the mediator. And also down in here, the same thing is happening. So everything down here really is excluded because you can't have the thermal scenario. Up here in this green territory, it's totally fine. It's just the current way we're accessing this is not direct detection predominantly. It's really the constraints on the mediator. But there's a lot of viable terrain that remains here, and a lot of places to look for improvements. All right, so again, you can ask how general is this simplified model? And we can perturb this in principle in various different ways. So adding additional heavy states, again, does nothing. Making the dark matter Dirac instead of Mayoral just introduces some order 1 corrections, but it's qualitatively identical. Nothing really changes in that scenario. You could imagine we fix our dark matter mass based on the choice of VEV, but you could in principle have a VEV set, or have a mass independent of this VEV, and just a smaller VEV to make some contribution. This ends up being a very small correction, and it doesn't really change much of the story because the freeze-out temperature is still just set totally by what the mass is, and that dictates a lot of the properties of the interaction strengths. If you add some additional global symmetry, this will increase the coupling, and you'll get stronger direct detection again. The one way you can modify this that is qualitatively different is if you add a CP violation in your scalar, so that you can actually turn on the direct detection and there are S-wave processes to annihilate. Adding a CP violating scalar that will complicate the standard model a lot, and it's a pretty dangerous thing to do, but in principle it's possible. And again, anything you add that's a light state is going to screw up our scenario. So with simplified models for the freeze-out story, we need our dark scalar and our dark matter to be the 2 lightest particles of the cycle. All right, so this is the work we're putting out now, but there's a lot of future options here, different ways to explore this territory. And one of the things we hope to do in the too distant time scale is to instead consider scalar dark matter coupled through the same portals instead of just the Majorana or the fermion case. The phenomenology of the thermally decoupled sectors, so things in the blue region of our epsilon versus T freeze-out plots. So what actually happens there? How can you do things predictively in that regime? I think is a very interesting subject. Further, you can have you can look at the cosmology of light dark matter. So below, in that sort of lower triangle, what sort of cosmological impacts are there on that scenario? I think there's a lot of opportunities. There's been a lot of attention on dark vector and trying to constrain dark vectors in every possible way, but light Higgs-mixed scalars are also a viable possibility. They have a fine-tuning problem in principle, but there's different ways, I think, to set new bounds on these scenarios. Although we did a sort of slightly simplified treatment of the thermal decoupling, it's a very interesting subject that should really be addressed in full, proper thermal field theory calculation. That's also hard, but it's an interesting question. Another interesting thing is in this scalar indirect detection signal, you have these bound states being formed. And that would in principle happen in these models generically. But if you are forming bound states, some of these can be stable. And what is the influence of a stable bound state on direct detection today, either in a vector scenario or another scenario? I think that's an interesting question that hasn't really been properly addressed. And there's many other interesting directions here. But the WIMP next door is a simple, plausible story for dark matter. These simplified models that I present here are minimal, bounded, constrained, general, but also pretty simple to construct, very simple Lagrangian. And they themselves are complete models. So you don't actually need some additional structure, although it does mimic additional structure, so you don't lose the robustness of the model. But they themselves could just be the entire story. Having the 2 sectors be thermally in thermal contact with one another mandates some sufficient connection to the standard model. And currently, direct detection is actually accessing this cosmological lower bound on the portal coupling. And in the future, it will become stronger and increase our direct detection sensitivities. I think there's a lot of opportunities for future experiments to access this model and these sectors. And that's all. Thank you.
Any more questions? Are you around for them?
Yeah.
So talk to me if you're interested in studying it. All right, let's thank Jerry.